Hello everyone. Today we are going to derive the stiffness matrix of a truss element. There are two videos that you have to watch in case if you have not watched them. The first video is on the basic concept behind trusses. It's just a 9 minutes video. You can check it through. I can give the link in the description below. And also there is one more video that is on how do you get the formula for strain energy as U. The formula for strain energy is U is equal to half into K into X squared. So the question here is how do you get this formula, because this formula is going to be the prerequisite in order to determine the stiffness matrix for a truss element. We are going to predominantly use this formula, so you have to become familiar with how do you actually use this. How is that you are actually getting this formula? Okay. All right. Now, without further delay, let us start the derivation for the stiffness matrix of a truss element so that we can do some wonderful analysis. As I said earlier, truss is a collection of bars. Truss will not bend, guys. It's not going to undergo any bending. You would have seen truss structures in airports, and they are actually made of pin joints. Pin joints allow rotation. However, the one member is preventing the rotation of the other member, so trusses are not going to bend. All right. Now let us start with a bar element, and let me try to define the strain energy for a bar element in the form of a matrix. Okay, this is the basic formula for strain energy, and I'm going to leverage and I'm going to build on this formula. So let me consider a simple one-dimensional bar element with two nodes. So this is a simple one-dimensional bar element with two nodes. And the displacement of the first nodal point along the x direction, of course, it's a bar, it's going to get displaced only along one direction. The displacement along the x direction is u1, and the displacement of the nodal point 2 along the x direction, it is u2. Now I can define something called as the actual deformation of the bar can be given as u2 difference u1 or u1 difference u2, in whatever way that you want to mention that, or u1 difference u2. So that is actual deformation of this bar. So let me now define the strain energy now. So strain energy U is given by 1/2 half. The stiffness of a bar is given by the expression AE over L. This is the formula for stiffness of the bar. So that's very simple, because stiffness is load by deflection, and you can write the load in terms of stress and the deflection in terms of strain. You get back this formula A by L. So it's not a big deal. It's very simple. You can check it through at the privacy of your room. Very simple. So it's 1/2 into stiffness, which is given by the expression A by L, into x squared. What is x squared? It is u1 difference u2 the whole square. So I can write this expression as u1 minus u2 the whole square. All right, whether it is u1 minus u2 the whole square or u2 minus u1 the whole square, it's not going to make any difference because there is a square term there. Usually it's u2 minus u1, but I want to do the derivation in a conventional manner. All right, and the next step, it's going to be 1/2. It is AE divided by L. I can write this term as u1 minus u2 into u1 minus u2, as that is u1 minus u2 the whole square. All right, in the next step, I'm going to say it's 1/2 into AE divided by L. What is this u1 minus u2? How do you write this value u1 minus u2? You can write this as 1 minus 1 u1 u2. All right, and you can also write exactly the same for the second term. It's 1 minus 1 u1 u2. So if you're going to do the matrix multiplication, when you do the matrix multiplication, you get back exactly the same step. So I can write u1 minus u2 in the form of a matrix like this. If you just do this matrix multiplication, you are going to get the same step as above. Now in the next step, it's 1/2. This step is a bit crucial. It's 1/2 into AE divided by L, which is a constant, AE divided by L. I'm going to interchange these two terms. The terms that I'm going to interchange, I'm going to bring this term here and I'm going to bring this term here, but I can only bring those terms, I can interchange those terms without violating the matrix multiplication by putting a transpose sign. So I can only do that without violating the matrix multiplication rule by putting a transpose sign. So in the next step, I can do that, but with a transpose, which means that I have to write the rows as columns. So now this becomes U1, U2, writing the column matrix as a row matrix now, and writing the row matrix 1 minus 1 as a column matrix now. That's right. Followed by 1 minus 1, U1, U2. That's right. Now all I'm going to do is I'm going to multiply this matrix, which is a 2 bar 1 matrix, and this matrix, which is a 1 bar 2 matrix. If I do the matrix multiplication, the resulting matrix is going to be a 2 bar 2 matrix. And what is the matrix if you multiply 1 minus 1 with 1 minus 1? What is the matrix that you're going to get? You're going to get 1 minus 1, first row into first column, and the first row into second column, the second row into first column, and the second row into second column, minus 1, 1. So this is the matrix that you will be getting if you do this matrix multiplication. You just have to take this and plug it here. Let me do that in the next step. It's going to be equal to, in the next step, it is 1 by 2. It is U transpose, because I'm writing the column as a row matrix. So I'll put U transpose into, I'm bringing this A by L, which is kept outside the matrix. You see, this A by L, it's a constant, so I can take it anywhere I want. I can shift it anywhere I want. I want to bring it here, so it becomes A by L 1 minus 1 minus 1 1, followed by U matrix. So I can finally, this is the expression for strain energy, but I can simply write this expression for strain energy U as 1 by 2 into U transpose, all right, into what is this term? What is this term? A by L 1 minus 1 minus 1 1. Quite obvious, that's the stiffness matrix of your bar element. So that's the stiffness matrix, all right, followed by U matrix, and this is going to be our star equation. So let me put a box for this term. So this is going to be our star equation. Now I'm going to derive the expression for strain energy in exactly the same manner for a truss member, and I'm going to come up with another star equation. Maybe I can call this as star equation number 1, and I'm going to come up with another expression for strain energy for a truss member, which means that truss member should be inclined just like this, okay? And I'm going to come up with the expression for strain energy. But before I do that, do you guys want a break for 5 minutes? You may fancy the idea of a cup of coffee. Take a break for 5 minutes and come back. All right. So now we are going to derive the strain expression for strain energy for a truss member. So here we go. So let me first construct a truss member. So it's inclined, and I have to be very careful when I say that this is an inclined structure, because I have to mention the angle. So let me mention the angle here. So the angle, it is theta. And please be very careful. The angle is always measured in the anti-clockwise direction. You see? I measured the angle in the anti-clockwise direction. You have to keep this at the back of your mind, because this is very, 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 very important when you try to solve the problems of trusses either for as an engineer or for every examination, it's very, very crucial. The angle should be reckoned along the anti-clockwise direction. And let me mention the nodal points here. This is going to be nodal point number 1, and this is going to be our nodal point number 2. Now, the truss is a structure that is subjected to loads, and the displacements of the nodal points are represented. I'm going to represent the displacement of the nodal points by this yellow color here. This is the displacement of the nodal point 1. It's not very visible. I will go with green. The displacement of the nodal point 1, say that's the displacement of nodal point 1, and that is Q1. And the displacement of the nodal point 2, it's like a bar. Either it gets compressed or it gets expanded, and that is Q2. All right, so I think you're all able to understand the displacement of nodal point 1 is Q1 and the displacement of nodal point 2 is Q2. Now what I'm going to do is I'm going to represent the displacement of the nodal point 1 Q1. I'm going to draw a highly zoomed up view of this displacement. So let me do that. So a highly zoomed up view of the displacement. So here we go. This is the zoomed up view of the displacement. Okay, all right, that is Q1, by the way. That is Q1, the displacement of the nodal point 1. All right, so this angle is measured in the anti-clockwise direction, and that is theta. Now I will call this, give names to this point. Let me call this point as A, and let me call this point as point B. And let me drop a perpendicular from the point B. All right, so that's a perpendicular that I am dropping from point B. And let me drop a horizontal from point A until they meet at the point C. Okay, now what I'm going to do is I'm going to draw a line by picking one point here in such a way, or I can do from here, I'm going to draw a line in such a way that if I can shift it anywhere I want. At one point it makes an angle of 90 degrees. Say I can shift it anywhere I want. At one point it's going to make an angle of 90 degrees. Let us say that at this point it is making an angle of 90 degrees. So this angle is going to be 90 degree. That's right, fine. Now this angle, obviously it's going to be 90 minus theta, so I will simply call that as alpha. So alpha is 90 minus theta, since this is also 90 degree. Now this point where it is meeting and making an angle of 90 degree, let me call that point as point D. All right, this is point D. Now I can write the displacement Q1. I can write the displacement Q1 as AD plus DB. And what is this AD for the triangle ADC? So for the triangle, for the right angled triangle ADC, can you just tell me what is this AD? So I can say what is, I can first let me tell what is cos theta. Cos theta is equal to adjacent side, which is AD, divided by the hypotenuse side, which is AC, and AC is the horizontal component of the displacement, which is U1. So I can say it is U1. So I can now work out for AD. AD is equal to U1 cos theta. That's right, U1 cos theta. I got the value for AD. In exactly the same manner, I can work out what should be DB. So in the triangle DBC, can you just tell me, this is also 90 degrees. So let us work out for what is cos alpha. Cos alpha is equal to, again, adjacent side divided by hypotenuse. Adjacent side is DB divided by the hypotenuse side, which is BC. BC is the hypotenuse side. And BC, you know, the vertical component of the displacement, and that is V1, the vertical component of the displacement. So cos alpha, so dB now becomes dB is equal to V1 into cos alpha, but alpha is 90 minus theta, so cos 90 minus theta is sine theta, so it's going to be V1 sine theta. So I got the value of dB. All I have to do is plug this value here for AD plus dB, so I can rewrite this expression as Q1 is equal to AD, which is U1 cos theta, plus dB, which is V1 sine theta. All right, so that is the expression for the displacement of the nodal point 1. In exactly the same manner, I can write the displacement for nodal point number 2, which is given by this expression Q2. The displacement of nodal point 2 is going to be U2 cos theta plus V2 sine theta. That's right. Having derived the expressions for displacements, now I can define the strain energy for a single truss element, which is actually a bar element. So in the next page, the expression for strain energy. Now we know what is the expression for strain energy, which we have already derived. It is going to be 1/2 into U transpose, that is the displacement matrix transpose, all right, followed by the stiffness matrix, followed by the displacement matrix. Now, how do I write this expression? Well, that comes from our star equation number 1. Where is our star equation number 1? Here we go, that the star equation number 1, here it is. So here the displacement for a truss element, it is Q transpose, the displacement matrix, and the stiffness matrix is just going to be the same. The displacement matrix is Q. All right, so that is clear. So in the next step, I'm going to say it is 1/2 into, what is this Q transpose? Well, it's Q1, Q2, right? That's right. But I have to write the Q matrix, Q1, Q2 in the form of a matrix. So let me do that. So here, let me try to write the Q1, Q2 in the form of a matrix. So here it is. It is Q1, Q2 can be written as CS 0, 0, 0, 0 CS followed by U1, V1, U2, V2. If you do these two matrix multiplication, you are going to end up with this equation. Well, I just forgot to tell you that C stands for the cos theta and S stands for the sine theta. So it becomes very easy. It is very conducive if I just use C and S. Now, how do I write this in matrix form? It's very simple, guys. So say, for example, you want to write Q1, which is Q1 is equal to U1 cos theta plus V1 sine theta. I just want to extend this. See, just trying to tell you how you write it in matrix form. Plus, you can say is to 0 into, I'm sorry, just 1 minute. It's going to be 0 into U2, all right, plus 0 into V2. Okay. So I'm just trying to include U2 and V2 here. That's all. Because for the second equation, you actually have U2 and V2. You can write the first equation in the form of a matrix. Very simple. How do you write that? Well, what is the coefficient of U1? It's cos theta. What is the coefficient of V1? It's sine theta. What is the coefficient of U2? It's 0. What is the coefficient of V2? It's 0. All right. Followed by U1, V1, U2, V2. You do exactly the same for Q2. It will be like 0 cos theta plus 0, I'm sorry, it's not 0 cos theta, it's 0 into U1. It's 0 into U1, so let me write that. This is going to be 0 into U1 plus 0 into V1 plus U2 into cos theta plus V2 into sine theta. You can write this in matrix form like 0, 0, CS, U1, V1, U2, V2. So you hit this matrix with this matrix, you end up with this equation. You hit this matrix with this matrix, you end up with this equation. All right, you are writing the two equations together like the one that I have mentioned here. Okay, so that's going to be Q1 Q2 is equal to CS0000 CS. So this matrix that enables you to transform between the actual displacements Q1 Q2 and the resolved components is called as the transformational matrix. Maybe you can call that as the matrix del. Okay, all right, so Q transpose then becomes, so Q transpose, so you can write this as Q matrix is equal to then the del transformational matrix into U matrix. So now I have to find Q transpose, which is equal to, if you want to find the transpose without violating the matrix rules, it should be U transpose into the transformational matrix del transpose. That's it. All right, so let me do that. The next step, here we go. All right, so let me do the next step here. U matrix is equal to 1 by 2 into Q transpose is U transpose into the transformational matrix del transpose, and the stiffness matrix for a bar element, it is A by L 1 minus 1 minus 1 1. How do I say that? Because truss is just a collection of bars, followed by the Q matrix, which is the del matrix into the U matrix. Okay, I think I don't have the luxury of space here. I will take a fresh page and I'm going to expand this in the next step. So U is equal to 1 by 2 into U transpose into del transpose. We know the transpose of the del matrix, so let me write that here, writing the rows as columns. CS 0 0 0 0 CS, okay, followed by A by L 1 minus 1 minus 1 1, followed by, it's going to be C del matrix CS 0 0 0 0 CS, followed by the U matrix U1 V1 U2 V2. That's it. Now let me do the matrix multiplication here. Maybe I will start by multiplying this 2 bar 2 matrix with this 2 bar 4 matrix. So the resulting matrix should be a 2 bar 4 matrix. So let me do the matrix multiplication now. So in the next step, it's going to be U is equal to 1 by 2 into U transpose, followed by CS 0 0 0 0 CS cos theta sin theta, followed by A by L. So let me do the matrix multiplication. What is the first row into the first column? 1 into C minus 1 into 0, it's C. First row into second column, 1 into S, the next term will be 0, okay. First row into third column, 1 into 0 minus 1 into C, minus C. First row into fourth column, it's going to be minus S, right? Second row into first column, it's going to be minus C. Second row into second column, it's going to be minus S. Second row into third column, which is going to be C. Second row into fourth column, it's going to be S, all right, followed by U. Now I'm going to multiply this matrix, which is a 4 bar 2 matrix, with this matrix, which is a 2 bar 4 matrix. So the resulting matrix is going to be a 4 bar 4 matrix. So let me do that in the next step. It's going to be U strain energy is equal to 1 by 2 into U transpose into Okay, let me do the matrix multiplication. A by L, I'm just bringing it outside the matrix. It's going to be A by L. Right, it's a 4 bar 4 matrix. So let me first construct a 4 bar 4 matrix, followed by U matrix. So here we go. You do this matrix multiplication. It's going to be first row into first column. It's going to be C square. First row into second column. It's going to be CS. First row into third column. I'm writing this matrix. You can check this at the privacy of your room. So it's first row into third column. It's going to be minus C square. First row into fourth column, it's going to be minus CS. It's minus CS. Now second row into the first column, it's CS. Second row into second column, it's going to be S square. Second row into third column, it's going to be minus CS. Second row into fourth column, it's again going to be minus S square. All right, it's minus S square. Now third row into first column, 0 into C plus minus C into minus C, it's going to be minus C square. Third row into second column, it's 0 into S, C into S, it's minus CS. Third row into third column, it's going to be C square. Third row into fourth column, it's going to be CS. Right, fourth row into first column, it's going to be 0 into C, S into minus C, it's minus CS. And the fourth row into second column, it's going to be minus S square. Fourth row into third column, it's going to be CS. Fourth row into fourth column, it's going to be S square. All right. Now this is going to be our star equation number 2. Sorry that I have taken a little bit of time to do the matrix multiplication, but I assure you that I'm going to give you a shortcut trick to remember this matrix. Okay, so now you compare the star equation number 1 with star equation number 2. So this is our star equation number 1. Our star equation number 2 that we have just derived is also of the same form. It's 1 by 2 into U transpose into A by L, followed by, there is a big 4 bar 4 matrix, which is like the C square, CS, minus C square, minus CS, CS, S square, minus CS, minus S square, minus C square, minus CS. Okay, then C square, CS, minus CS, minus S square, CS, S square, followed by this U matrix. This is our star equation number 2. You compare them. So in place of stiffness matrix, what is there? In place of stiffness matrix, you have this big 4 bar 4 matrix. So the conclusion is our stiffness matrix for a truss element should be this A by L, the 4 bar 4 matrix. All right. So that is the formula for stiffness matrix of a truss element. Okay, finally, how do you easily remember this matrix? It's very simple. So the formula for stiffness matrix, you can easily remember this matrix in this manner. So here we go. You first construct the 4 bar 4 matrix. All you have to remember is remember C square and CS. This is what you have to remember. Okay, it's very simple. I used to remember this way. See whether this trick actually works for you. Bring the CS here, and instead of C squared, write S squared. That's all. Okay. Then multiply the first row, this term, by minus sign and write minus C square, and this term by minus sign and write minus CS. and multiply this by minus and write minus CS, and multiply this by minus and write minus S square. Then multiply the first row throughout by minus sign and write it in the third row. It's minus C square. It's minus CS is C square CS. Then multiply the second row completely by minus sign and write it in the fourth row. It's minus CS minus S square. It's CS S square. So you can check the stiffness matrix for whether it is actually correct. You can see C squared CS minus C squared minus CS, C squared CS minus C squared minus CS. It's CS S squared, CS S squared minus CS minus S squared. It's going to be minus C squared minus CS minus C squared minus CS, C squared CS. It's going to be minus CS minus S squared minus CS minus S squared CS S squared. That's it. So this is the formula for the stiffness matrix. Also, the important thing that you have to remember is when you have a truss member, and this is nodal point 1, nodal point 2, always mention the theta in the anticlockwise direction, that too from the least nodal points. Okay, that too from the least nodal points. Suppose now this is nodal point 1, this is nodal point 2. So what is the value of theta here? It's 0. Now the next example, suppose you go in this direction. This is nodal point 1, this is nodal point 2. You have to measure theta, put the coordinate and measure it in the anticlockwise direction. Now the theta is 180 degrees. Okay. Suppose you have 1, 2. So what is theta? It's a 90 degree. Suppose you have 1, 2. You put it in the least coordinate and measure it in the anticlockwise direction. 180 plus 90. So 180 degree plus 90 degree, it's going to be 270 degree. So that's the value of theta. All right. So it's 180 plus 90. So this is the procedure to measure the value of theta. So this is the formula for stiffness matrix that you have for a truss element that you are going to use to solve the problems. Thank you for your patience. Thank you so much.